Hello, class of Physics 7C. Today we're going to talk about rotation of rigid bodies. Okay, so in this chapter, we're going to learn about rotation in terms of angular coordinate, angular velocity, and angular acceleration. They have direct analog to what we have learned in terms of displacement, velocity, and acceleration. We're talking about linear motions, one objects are translating. And here we're basically redefining all of these concepts in the angular space. We're going to talk about how to analyze rigid body rotation when angular acceleration is constant. We're going to talk about the meaning of the body's moment of inertia, which is an analog of mass, about a rotation axis and how it is related to rotational kinetic energy, and also actually how to calculate the moment of inertia of rigid bodies. Okay, so let's get started. So in this chapter, because we're talking about rotation, objects are not points anymore. Um, we know that real world rotations can be very complicated because of stretching and twisting of bodies. But for now, we'll assume that the rotating body is perfectly rigid. Um, this would be the assumption throughout this chapter. Okay, we're talking about a body that's fully rigid. Okay, there are many examples of perfectly rigid objects that are rotating. For example, the airplanes, propellers, a revolving door, a ceiling fan. All of these are perfectly rigid bodies that has the rotating motions. Okay, so to give you another example, if you have half-filled bottles of water, and in this case, when bottles of water starts rotating, the water inside will actually start to redistribute their positions with respect to the bottle. In this case, this half-filled bottle is not considered a rigid body. However, if replace the water by pure resin and stays put in this bottle, in that case, this half-filled bottle becomes a rigid body. Okay, it really depends on whether there's a redistribution of the internal mass inside the object while it's rotating. Okay, so very simply speaking, a rigid body is something that there are no moving parts, there's no redistribution of mass. Okay, so let's first define angular coordinate. That's how we actually define angle while something is rotating. Okay, here we're giving an example of a car's speedometer's needle that rotates about a fixed axis. And here we're assigning the plane where the needle lies in is the x and y plane. The x-axis points to the right, and the y-axis points up. And here the needle is actually rotating counterclockwise here. As you can see here, it's rotating counterclockwise in this direction. And here, how we define the angle would be from the x-axis here. All of you should be familiar with this this angular theta because we have used this to actually decompose vectors onto the x and y axis. So this is actually the same theta that specifies the needle's rotational position. Okay, just like a vector, right? Here it is an actual rigid body that rotates to a certain theta. Okay, And here, another important thing here is for rotation, you'll always have an axis of rotation. And in this case, this axis of rotation passed through the origin that we have chosen, which coincide with the actual physical axis of rotation. And the direction of this axis is actually, in this case, pointing out of the plane, out of the page. If you look at the screen, is pointing actually toward you and out of the screen. Okay, that is basically here. You don't really see it because it's perpendicular to the screen and it's pointing outward. Okay, and this angular rotation is revolving around this z-axis that points out of the screen. Okay, so this is basically the angular coordinate they're working with to define the angle theta for rotation. So the angular coordinate and these angles are not new concepts to you, because we have learned how to decompose a vector under this kind of a coordination before. But the thing here, the thing is, the unit of angle, a more natural way to define the unit of angle is actually by using radian. Okay, and here the radian is actually defined by the arc distance, the ratio of the arc distance s. That's here, basically this here. This is arc distance. If an angular rotation goes from here, from A to B, and the arc distance is basically s here. Okay, and the angle here is defined by the arc distance or the arc length s divided by the radius. Okay, and under this definition, the theta has a unit of radian. Okay, so basically, as you can see, we know for full rotation here, a full revolution, right? That the s is equal, basically the circumference equal to 2 times pi, right, times r, right? And in this case, the angle theta, if it does a full revolution, would be c, that's the whole circumference, divided by the radius, right? And that would be 2 pi r divided by the radius and equal to 2 pi. Okay, that's basically what we say here. When you rotate, do a full, complete revolution, that's old definition using degrees, that'd be 360 degrees, and then basically in our new unit, that is a radian, that will be 2 pi radians. Okay, and I think this is not a completely new concept to you. So 360 degree is 2 pi radians, and for pi, that will be equal to 180 degrees, right? And for pi divided by 2, that will be 90 degrees. Okay, so this is how we basically convert the radians and the degrees, the old definition. Okay, and here we're using this unit, and 1 radian is when you have this arc length that is exactly equal to the radius. Right, now we basically know this new unit that's called the radian, that basically defines the angle, that gives a unit to the angle that we're talking about here. All right, the next would be angular velocity, right? So when we were talking about linear motion, right, we have displacement that has SI unit of a meter, right? And then we talk about the velocity or speed. And in that case, the velocity or speed is basically a time derivative of the displacement. And here, when we're talking about angular velocity, then it would be the same thing. We're talking about an first we first would calculate the average angular velocity. That would be at time 1 and time 2, how much angle that has been rotated by this speedometer needle. That will be delta theta here and divided by this time interval delta t. Okay, so that would be the average angular velocity. Basically, the angular displacement here that replaces a linear displacement. Delta theta is equal to theta 2 minus theta 1 and divided by the time interval. That gives you the angular velocity. And here is worth noting that the subscript z here means that the rotation is about the z-axis. Okay, for any given rotation, there's always one axis that this object, this specific rotation that's actually revolving around. Okay, and then here, this axis is basically the z-axis that's pointing out of the plane from this point here. Okay, and of course, and when we talk about angular velocity, we choose the angle theta to increase in the counterclockwise rotation. This is just a definition. So basically, if your angle goes, you have a rotation that goes the counterclock direction, that goes this direction, then this theta would increase, and so the angular velocity is positive, right? Okay, if it goes clockwise, and then the theta decreases, so the angular velocity is negative. Okay, so that's basically right. If it just goes clockwise, then the delta theta is actually a negative value, right? That's by definition that we define the theta increases in the counterclockwise direction and decreases in the basically in the clockwise direction, right? Okay, so this is basically how we actually define the positivity and negativity of our angular displacement theta. Okay, this is just a convention that we follow. Okay. And now, of course, we would, when we take the time limit, the delta t, the time interval to 0 to infinitesimally small time interval, in that case, we would be getting instantaneous angular velocity. That is basically as taking a limit as the delta t goes to 0, both of these two. Okay, and that's basically giving us that the instantaneous angular velocity is a time derivative of theta, which is the angular displacement for a certain rotation. Okay, and in the rest of the chapter, when we are talking about angular velocity, we always mean the instantaneously and instantaneous angular velocity, not the average one. Okay, not the average one. And here we have the z subscript, means the object is revolving around the z-axis that we defined. And angular velocity, as we just talked before, it can be positive, it can be negative, depending on the direction in which the rigid body is rotating. Okay, and we'll talk about that in the next couple of slides, right? So so far we've talked about angular displacement and how it is defined in a angular coordinate. And now we also talk about the angular velocity that would actually be a time derivative of the angular displacement, right? And there's always, for any angular motion, any a rotational motion, there's always an axis that this motion revolves around. We want to actually carry that. And also next we're going to talk about the how we define whether an angular velocity is positive or negative. Okay, just like linear velocity, angular velocity is actually a vector. So the angular velocity is defined as a vector whose direction is given by the right-hand rule. As shown here, if this gear is rotating counterclockwise, right? And basically how you define the direction of this angular velocity is by curling your right hands in the direction of the rotation, okay? Basically here, right? And your thumb will point to the direction where that direction is basically the direction of this angular velocity. So if you have a counterclockwise rotation for this gear here, you do the right hand rule, and then you would find that this angular velocity is pointing upward, okay? And on the other hand, if it is rotating clockwise, right, and then you do your right hand rule again, right, and it's basically you will find that your thumb is actually pointing downward. And in this case, that will be an opposite direction to the counterclockwise rotation. Okay. Basically, your right thumb points in the direction of the angular velocity, and this is called the right-hand rule. We use that to define direction. Okay, so now we know that the magnitude of the angular velocity is basically a time derivative of the angular displacement, and the direction is defined by the right-hand rule. Okay. And next, right? So the angular velocity again is a vector. The sign of the angular velocity, along a certain z-axis, and depends on whether it's this direction is the same direction as the positive z direction, right? In this case, this gear is rotating counterclockwise, and you use the right-hand rule. So the angular velocity is pointing upward, which actually has a positive component that projected along the z-axis, and then of course the omega z, that is the component, the z component of the vector of the angular velocity vector would be a positive value. Okay. In the other case, if this angular velocity pointing to the negative z direction, and then the angular velocity omega z would be a negative value. Okay, so right, so we've talked about angular displacement, we've talked about angular velocity. We know angular velocity is actually a vector quantity, and now just like when we were talking about linear motions, right? So we have displacement, and then we talk about the time derivative of the displacement that gives you the velocity or the speed. And then after that, we would talk about the time rate change of the velocity, that is basically acceleration. And similar here, for angular velocity, if you look at the time rate change of the angular velocity, and that is basically defined here as well in the same way as linear acceleration. That would basically from time t1 to time t2 in the time interval of delta t, t2 minus t1, the angular velocity changes from omega 1 to omega 2. And that change, delta omega, and divided by the time interval t, would actually be the angular acceleration. Okay, this is the same definition as, except here, same way that we define acceleration for velocity. And for the instantaneous angular acceleration, we're basically taking a limit where delta t goes to 0. And in that case, we're basically taking a time derivative of the angular velocity. And here, please note that for linear acceleration, we're using a to denote this quantity. And here we're using alpha for the angular acceleration. Okay. And of course, angular acceleration is a vector as well, right? Because angular velocity is a vector, right? So the time derivative of a vector quantity would be a vector quantity as well. So in this case, if the angular acceleration aligns with the angular velocity, if they point to the same direction, point in the same direction, then the rotation is actually speeding up, right? That's basically, you can think about the omega is actually getting longer and longer, right, in magnitude, right? And that's basically meaning the speed of rotation is getting larger and larger. In the other case, if the angular acceleration and the angular velocity are in the opposite directions, then as a function of time, as you pass, pass a short time interval t, right, this omega vector is going to become shorter. And that just means the rotation is slowing down. Basically, the speed of rotation is decreasing, right? Because this vector omega is getting shorter due to the fact that you have angular acceleration that points in the opposite direction. Okay, so then here is basically we've talked about how to define a rotation under the angular coordinate. I'll talk about how to define angular velocity. That would be the time derivative of the angular displacement, theta, d theta versus dt. And then we talk about the direction of the angular velocity follows the right-hand rule. You basically curl your hand around the rotation. That's basically the direction of the angular velocity. And then we talked about that the time rate change of the angular velocity is the angular acceleration, and of course, it is a vector quantity, and basically when they're in alignment, pointing in the same direction, then the rotation speed up. And if they point in the opposite direction, the rotation slow down. Okay. So when we talk about linear motion with constant linear acceleration, we basically have a series of kinematic equations that relays this constant acceleration and t, and also velocity, and also the distance that they travel, right? So remember all that. So basically, we want to know these as well. We want to know as a function of t how omega z changes, right? That's basically the angular velocity, and also how much angular displacement that has undergone during the period of this angular constant angular acceleration. So the first equation will be a linear ramp up of the speed, and here's a linear ramp up of the angular velocity, right? Now basically, you have the initial angular velocity plus the constant angular acceleration times t. Okay, um, that's an exact analog of the linear velocity. Okay. And then for the angular displacement, then at a certain t, that will be your initial angular displacement theta zero plus the linear term, that is the initial angular velocity, and times t plus half time the angular acceleration times t to the second power. Okay, that is again has an exact analog to the linear motion. Okay, and here this equation relates the angular velocity to the change to the angular displacement and angular acceleration. Okay, so this is it follows exactly the same form as the linear equation. And this one as well. And this is basically the trapezoid rule that we talked about, right? So we talk about as a function of t, right? If you have omega here, and you start with omega 0, and you ended up with, you know, omega z, and the area under this curve would be half time omega 0 plus omega z times t. Okay, this is the same with the linear motion as well, right? Okay, t versus v, and except here that we're talking about linear displacement, and here we're talking about angular displacement. All right. So now we basically have learned all the kinematic equations when you have a constant acceleration, a constant angular acceleration, okay, with a fixed axis rotation. Okay, so and the equation are exactly the same as the linear kinematic equation, linear motion kinematic equations, except that you basically swap v to omega, and you change x to theta. Okay, and you change a to alpha. The rest stays the same. Okay. Okay, and now let's relate the linear and the angular kinetics, right? For a point here that's basically rotating, revolving around point zero, point, the origin here, not zero, the origin, and if its distance from the rotation axis is r, and it is if the angular speed is omega, and then the velocity would just be the radius times the angular velocity or angular speed. Okay, so they have this multiplication relationship, right? R time omega. Okay. So that's basically how the linear and angular speed are actually related. Okay. So next, then for for a rotation that has actually that is not a constant velocity, constant angular velocity rotation, when we have an angular acceleration, then here for this velocity, how it changes as a function of time would actually have two components. One component would actually be the tangential acceleration. That would basically be the radius time the angular acceleration alpha here. Okay, the radius time the angular acceleration. That would be the tangential acceleration for this point P. And don't forget that as this point is actually revolving, this V is actually changing its direction as well. So there is a centripetal acceleration, the radial acceleration as well. We've learned that its magnitude is V squared divided by R. And here, if we plug in what we just learned in the last slide, is V equal to omega times R. And here, that will be omega squared, R squared divided by R. And we come up with a new equation that a centripetal acceleration is omega squared times R. Okay, so here is a pictorial representation of what the total acceleration is. You have the tangential acceleration that's dependent on the angular acceleration, and also a radial or a centripetal acceleration. That's because the velocity is changing its direction as it's rotating. Okay, right? And now it's worth noting that the importance of using radians, but not degrees, is that for radians, it directly relates the angular the arc length that this needle travels with the angular displacement by a multiplication of R. So as here, for example, if it goes by pi over 3, that is basically 60 degrees, then you use this equation, that's how far it has traveled. It is incorrect to use 60 degree here, right? That's just not sensible. This is incorrect, right? Okay, this is why we want to use the radian unit as opposed to the degrees. Okay. Okay, now we're going to introduce another new concept, a new physical quantity, right? Let's think about what we have learned so far, right? What kind of, we basically have related all the kinematic equations with the kinematic equation in the angular space, in the rotational space, right? We basically have x, that's the linear displacement, that has direct analog, that's basically theta in the rotational space. And we have velocity v, that becomes omega in the that's the angular velocity. And we also have the linear acceleration a. In this case, the direct analog in the rotational space, that will be alpha. That will be angular acceleration, right? So the next thing is, once we finish talking about all the kinematics, the next important thing is to talk about dynamics, right? So basically, the dynamics for us is what we learned in chapter 4, right? That's the first equation that we talk about, right? F equal to ma, right? So, and here the thing is, we want to know what is m in the angular space when we talk about rotation. And its direct analog is called the moment of inertia. And the moment of inertia, we use a capital letter I to denote it. It is obtained by multiplying the mass of each particle by the square of its distance from the axis of rotation, and adding these products up. As shown here, this is I is equal to, if you have M1, M2, then dot all the other particles, you basically have the mass times how far this particle is away from this from the rotating axis, the rotational axis. Remember that the distance here is basically defined as the perpendicular distances of the particle from the rotational axis. That is the closest distance of this particle from the axis. Okay, you sum all of them up. The sigma over I means to sum all of these products up. And that basically gives you the moment of inertia of the system. Okay. Then let's look at in the case when this particle system is revolving around an axis with a fixed axis and also with an angular speed of omega, right? So the total kinetic energy is basically half mv squared sum over all of them, all the i's, right? So, and this is half mi vi squared. That would be the kinetic energy of a certain of one of the particle, right? And here, because we're talking about that how to relate the linear velocity with the angular velocity, right? So that will be omega times Ri. That will be the distance from that particle to the axis, right? Okay, is again, please note that the whole thing is a rigid body, right? No matter how many particles they are, their relative position to each other and also to the axis does not change while they're rotating. So these are fixed values for certain force for a given particle, and they're all rotating at the same speed because it's a rigid body, right? And then with this, we can pull the omega out because it's a common factor. And here, what's left behind is sigma mi ri square. Okay, and this new term here, the sum over mi times ri square, that is basically I. That basically exactly is the moment of inertia that we just defined. Okay, so let's look at this form, right? The kinetic energy for a given rotation of a rigid body system will be half time the moment of inertia and time the angular speed square. Okay, so this again is a direct analog to the linear kinetic energy, right? So this is half I omega square, and for the linear motion you have half mv square, right? So and omega and v are direct analog, right? And the rotational inertia or the moment of inertia is exactly an analog of the translational inertia. That's the mass here. Okay, so so basically, so far we've learned, you know, in the rotational space, what angular velocity is. We also derived what the kinetic energy for a rotational rigid body is, and that is basically half times the moment of inertia times omega squared. And the moment of inertia is defined as a sum over all the product of the mass of times the square of the distance of that mass from the axis. Okay, so and basically that's basically the moments of inertia. Okay, so let's do a little bit of thought experiment. Here's an apparatus that's free to rotate around the vertical axis, and here we want to reduce the moment of inertia, and basically we move them very close to the rotating axis and lock the two equal masses cylinder close to the center of horizontal shaft, right? Okay, the mass close to the axis, that gives you a smaller moment of inertia, and it's easy to start the apparatus rotating, okay? And here's an apparatus that's free to rotate around a vertical axis. Again, the same. If you to increase the moment of inertia, you can basically pull them apart, right? Basically, that's increasing the MI RI square, right? So basically, in this case, this stays the same, right? It doesn't change, but the RI is actually increasing. So therefore, the total moment of inertia is actually increasing as you pull the two masses away from the center of the horizontal shaft, right? So using some real world examples, a hummingbird has very small mass, and also the size of the wings are small as well. Therefore, it has a very small moment of inertia. So that's why the hummingbird can actually flap its wings very rapidly. Around 70 beats per second, whereas if you have a very large bird like this condor here, and you can think about as it extends the wings, that will be actually 2 to 3 meters long, and also is much heavier than a hummingbird, and then it would have a much greater moment of inertia. And then that's why these large birds wouldn't be able to flap their wings very rapidly. Typically, that's around 1 beat per second. That's actually pretty fast for these large birds. Okay, so right now, how do we actually calculate the moment of inertia for a object of a given shape, right? Right. So previously, the equation that we showed, right, are basically when we have a series of point object, series of particles, we basically can sum them up discretely. Whereas in the case, if we have, say, a disk or a cylinder here, this is a cylinder, and this is a disk, and how do we actually calculate the moment of inertia, right? And it actually can be found by integrating this. And r squared is basically the same, the distance of, and here this rho dv, that's basically a small mass right here, right? And that's basically when you have the sigma over r squared m, right? And basically turn that into a integral form, that will be r squared dm, right? And the dm is basically the rho is the density time dv. Okay, let's together derive the moment of inertia of a solid disk cylinder, right? And here, let's look at first, if the mass of the cylinder is m, and that the rho is basically m divided by v disk. Let's look at what the volume is, how is it calculated. That will be the pi r squared times h, right? That will be the thickness here, right? Thickness of this cylinder, h, right? Pi r squared will be the area, right? And then if we do a derivative, that will be dv, and here r will be the one that can be changed. That will be 2 by h r dr, right? Okay. And then we basically can put this into this equation, right? So the rho pulls out, and dv, we can replace that by this, right? And then we pull the constant out, right, to here, the v disk, and we know what it is, right? That, and here, this is actually, in this here, that's actually r square. The disk, that's not actually a changing value, okay? And then we basically r to the third dr, and then the integration of this will be 1/4 of r to the fourth, 0 to r, okay? And here this is r square, and then basically it gives the moment of inertia is half of the total mass of the cylinder time the outer radius raised to the second power. Okay, that's basically how we define, how we derive that what the moment of inertia of this cylinder is if the axis is lying in the center of the cylinder, along the center of the cylinder. Okay, so what about the moment of inertia of a solid sphere? Okay, here we can actually use the result we have just derived for a disk, right? Because for a sphere, we can actually chop this sphere into discrete disks. Okay, right? So we chop them into little disks, and let's find the for disk here, right? The radius is dependent on how far it is away from the xy plane. That's z here, right? That's the z-axis. On the y square, because of this is a right angle triangle that has a right angle here, then y squared is equal to r squared minus z squared, okay? Because there's a right angle here, right? And then in this case, the mass here would be rho times pi y squared, that's the radius pi dz, right? Okay. And the angular momentum, the moment of inertia for this little disk would basically be half the mass time y squared, right? Right, and sorry, this is not here. This is not supposed to be here. Di times y squared. Remember that, right? So the angular the moment of inertia for a disk or a cylinder is half mr squared, right? That's basically how here the the moment of inertia of this little disk here would be half dm times y squared. Y is basically the radius here, and then we put all of these into it. That basically arrived at this equation with y raised to the fourth power dz. Okay, what we want to do next is basically calculate the total moment of inertia. Basically, we're integrating all of these small disks from negative r to positive r, right? That will be half time the density times pi, and here we use this equation, y squared equal to r squared minus z squared, and put it in here, and dz, okay? And now we have basically the z that will be integrated out, and this whole thing is equal to a divided by 15 rho pi r to the fifth, okay? So here you can actually, here I write out how this thing is derived. You basically expand this term, and this is a polynomial that will be integrated, and you will end up having all of these constants in front of r to the fifth square that give you this, okay? Give you this result. And the other thing is the rho here, right? The density will be the total mass of the sphere divided by the volume. The volume would be 4/3 of pi time the radius of the sphere raised to the third power. That would be, then it will giving you 2/5 of mr squared. Okay, that's how the moment of inertia of a solid sphere is derived. There are all others. You have this basically a rod that's 1/12 of ml squared, given the length is L. If you move the axis to one side, that will be 1/3 ml squared. Okay, right? And this is for rectangular plates. Have slightly different equations and all that. I'm not gonna go through this. You can actually find all of these formula in the table in the book. Okay, so right, and now let me introduce you a parallel axis theorem that basically, given this, it would be easier for you to calculate what the moment of inertia is for a given object when you are moving the axis around. Okay, it is called the parallel axis theorem. It's talking about the moment of inertia of a body about an axis through its center of mass, and the moment of inertia about any other axis parallel to the original axis. And what it states is that when you move the axis away from the center of mass, while it's, as long as it's still parallel to the original axis, then the moment of inertia would be equal to the moment of inertia when you have the axis travel through the center of mass plus the total mass times the distance squared, how far the two axes are separated apart. Okay, let's derive this parallel axis theorem together. And here, let's draw a a rigid body here, and assume that is originally there's an axis C that actually travel through the center of mass. And then now we move the axis D, distance of D away from it. And then we want to know what would be the angular, the moment of inertia is after around the new axis L. Okay, so let's work this out. Is basically the moment of inertia will be sum over all the little masses delta m times basically here the r is basically the distance of this little volume or mass to the original c-axis, right? And because it's moved the d distance up, that will be r minus d raised to the second power. Then il here, the moment of inertia would just be r squared minus 2rd plus d squared, right? And then you basically expand this into three expressions. And the first one that we can recognize, and the second one term and the third term right here. It is very important to know because the origin C is the center of mass. Actually, small c here, the small c is the center of mass. By definition, then the sum of all the little masses time r would equal to 0. Okay, that's because this axis to travel through the center of mass, right? So that basically tells you the first moment of how the mass would actually be 0. So therefore, this term actually drops, and you have basically the moment of inertia around the new axis to be the sigma is basically the first term and then second term, right? And the first term will actually just be the moment inertia of about c, about this axis that travel through the passes through um, the center of mass, and then d is the distance d away from the c and time m, right? Okay, so that's how this parallel axis theorem is can be derived. Okay, can be proved and derived. Let's apply the parallel axis theorem to these these two cases. One, when you have a rod, right? So you can actually calculate. We're not gonna. Sorry, this is one here. Right? For this one, this axis passes through this rod, the center of the rod. That's basically where the center of mass is located. And that, if you work out the mass, that will be 1/12 of ml squared. Okay, and then we want to know if you move this axis to one end of it, what the angular momentum would be, right? That would actually be the I1, right? That's basically the IC, the 1/12 of the ml squared plus m times the distance. It will be L divided by 2. That will be the D, right? D squared. The D is L divided by 2. And then we pull the ml squared out, and that will be 1/12 plus 1/4. That's 1/3 of ml squared. So basically, once we calculate what the the moment of inertia is around an axis that travel through the center of mass, then for any axis that's parallel to it, we can basically use the parallel axis theorem to actually derive what this new moment of inertia is. Okay. So here's a table of large fraction of all the rigid objects we're gonna work with. So you don't have to really memorize all of these. You can always look it up in a table that give you all of these results. Okay, so. All right, so this is the end of the class. Thank you, and class is dismissed.